Hello everyone, welcome back. In this video, we'll be taking a look at theorems in field axioms. So let's start with the first one. We're told let F be any field and prove that for all x in the field that the additive neutral times any element in the field is equal to the additive neutral, that is 0.x is equal to 0. So let's see how we can begin this proof. So I'm going to start it this way. Write it as 0 plus 0 is equal to 0. Well, we know this is true. 0 plus 0 is equal to 0. And let's multiply this with x. This is a valid step as we're multiplying both sides by x. So we can do this. Then this is equal to 0.x plus 0.x is equal to 0.x. This is a valid step. This is because of the ninth field axiom which we did in the previous video by distributivity. So we're just distributing x on the left hand side to the elements inside the brackets. Next we're gonna add 0.x to both sides. So this is the additive inverse. So the additive inverse of 0.x is negative 0.x. So from the previous video, we know that the additive inverse, when you add an element to its additive inverse, we get 0. So this part boils down to 0 and this part also simplifies down to 0. So we get 0.x plus 0 is equal to 0. And we know from the previous video that by the additive neutral, since we're adding 0 to the left hand side and 0 is the additive neutral, when we add the additive neutral to any element in the field, we get the element itself. So we get 0.x is equal to 0, which is what we needed to show. So that completes the proof of the first theorem. Let's take a look at the second one. Well, we're told to show that minus x is equal to the same, is the same as negative 1 dot x. So basically we need to show, remember that when you're writing proofs, it's always good to write down what we need to show. It helps you direct in a particular train of thought. So we need to show x plus minus 1 dot x is equal to 0. Well, how did I get this stuff? So, well, when you're writing proofs, remember that you should always do some scratch work. In a textbook, it seems like the proof is perfectly written and it's perfectly done and the author knows everything. But trust me that there's always scratch work which is done, which is then manipulated in such a way to show that it is the proof. So let's see what I mean by this. So we need to show that minus x, so this is my scratch work, minus x, and in your scratch work you can do whatever you want. This won't be there in the final proof. We need to show this. So I'm going to just take this to this side. So we get x plus minus 1 dot x is equal to 0. So if we can show this is true, then this is automatically true. And since this is the scratch work, we don't need to show any 1, so I'm just going to cross it out. So we need to show this. Well, let's see how we can do that. So I'm going to write it this way: 1 dot x plus minus 1 dot x is equal to 0. I just changed x to 1 dot x. This is because of by multiplicative neutral or the multiplicative identity. When you multiply any element by the multiplicative neutral, which is 1 in this case, you get the element itself. So now I'm going to use distributivity, the ninth field axiom, to show that 1 plus minus 1 dot x is equal to 0. Remember, I'm just removing this x by distributivity, which is a field axiom, And we know 1 plus minus 1 by the additive inverse is 0. So we get 0 dot x equals to 0, 0 dot x equals 0. And remember, this is all the right hand side. I'm trying to manipulate the left hand side to equal to the right hand side. So I'm trying to make the left hand side to be 0. And then we're done with the proof. So 0 dot x by multiplicative neutral. Oh, no. By the previous theorem, I'm sorry about that. By the previous theorem, which we did, which was part A, we're told that 0 dot x is equal to 0 indeed. Not by the multiplicative neutral, I'm sorry about that. So 0 dot x is equal to 0 indeed, and 0 is equal to the right hand side, which is 0. And we're done with the proof. So look at how I built on my previous theorem and my previous proof to help me prove this part. So this is going to be a common theme in this course, where we should be able to use the previous theorems and previous proofs to help us prove the theorems we'll do later in the course. So theorems are our friends. We should always treat them. You guys should be happy when you see theorems, as they make your life easier when you're proving theorems in the future. So let's take a look at this one. Okay, how are we going to do this? We've been told to show that AB inverse is the same as A inverse B inverse. Okay, let's see how. Okay, we need to show. Well, I haven't done my scratch work yet, so I don't know what I need to show yet. So let's see what we need to show. So I'm going to do my scratch work right here. Okay, so AB inverse is the same as 1 over A over B. I like to write it this way, which is better than writing it as AB inverse. As you can see what's going on, A inverse, B inverse. So I'm just going to take this AB to the right hand side. This might seem like cheating, but it really isn't. This is the only way you can prove this theorems in the field axioms. So we need to show that AB and A multiplied by A inverse B inverse is equal to 1 by using the field axioms. So let's see how we can do that. Okay, so AB, I'm going to write it this way, B inverse. This is because multiplication is associative, which is a field axiom. So you can rearrange the brackets however you want. Then I'm going to write this as A inverse B inverse, right? Because multiplication is commutative, so I'm just switching the order of B and A inverse. And we know A times A inverse is equal to 1. And well, before we write that, let me just write it this way. This is because multiplication is associative. I'm just rearranging the brackets. Then we know that A times A inverse is 1 and B times B inverse is 1 also by the multiplicative inverse, which is also a field axiom. So see how I'm using the axioms the 9 axioms the 9 field axioms, which are the foundations of the field, to prove theorems in the field. And we know that 1 dot 1 is equal to 1 by multiplicative neutral. Anything times 1 is itself. So 1 dot 1 is equal to 1. And that's what we needed to show. I've manipulated the left hand side to make it equal to the right hand side. So the left hand side is equal to the right hand side. And we're done with the theorem. Okay, let's take a look at another one. Okay, this is a if and only if proof. Because of the double arrow, the two directional arrow, so we have to prove both directions. So if you remember from our first video, that when we're proving if and only if statements, that we can always assume the first part, and we need to prove the second part. We need to prove x equals to y or x equals minus y. So let's see how we can go about that. So I'm assuming x squared is equal to y squared because this is a if and only if proof, and x squared minus y squared is equal to 0. Right? I'm just adding negative y squared to both sides of the equation, and I get this. And we can further write this as x minus y, x plus y by difference of two squares. And this, just equating them to 0, we get it as x equals to y, x equals minus y. Well, it may seem really easy, and it is easy. There's nothing complicated about this. About proving theorems in field axioms. These theorems are much easier to prove than the theorems we'll do later in the course about limits. So when we're proving the other direction, we can assume x equals to y, x equals negative y. Well, now I'm gonna first deal with this case, and I'm gonna square both sides. X squared equals y squared, and we're done with this. And x equals negative y. Same thing, I'm gonna square both sides. But since we have a negative, it's gonna be a bit more complicated, but it's the same thing. We get x squared equals, because this is the same as negative y squared is the same as negative y times negative y, which is the same as negative 1 square y square by distributivity, which is the same as 1 dot y, which is the same as y by multiplicative neutral, or the multiplicative identity. So the end, this should be y square. So we get x squared equals y squared, and we're done with the proof. So we're done with both the directions of the proof, and we're done with this theorem. Well, now let's take a look at the last theorem for this video. So we're told to prove that minus a times minus b is the same as ab. So we need to show that minus a minus b plus minus ab is equal to 0. So what I did in my scratch work, I just took this ab to the other side of the equation. So let's see how we can do this. Well, this is the same as minus a minus b plus b equals 0. This is by distributivity. I'm just removing the a's and then I'm undistributing them. Right. So this is by the ninth field axiom, which is valid, and we can do this. And this is the same as plus minus b equals 0 by addition is commutative. I'm just switching the places, which is the same as this by additive inverse, and this is the same as, remember we proved it in the first part of the video, 0 dot x equals 0. So 0 dot any element is 0, 0 equals 0. The left hand side is equal to the right hand side. So we manipulated the left hand side to be equal to the right hand side. So we're done with the proof. So as you have noticed, proving theorems in field axioms using field axioms is pretty simple. So hope you have enjoyed the video. See you next.